And the next topic is the transaction states. So generally every transaction will move from one state to the other state during its execution. So here basically we have 5 states. The first one is the active state, partially committed state, failed state, aborted state, and committed state. So initially when the transaction starts its execution, so it will move to the active state, and from active state, so it will move to partially committed state, so when it completes the last instruction, and from partial committed state it moves to the committed state when it executes commit state. So you see here in the diagram, you can see in the diagram. So this is the active state. So when the transaction starts its initial instruction, execution of initial execution, so it will be in this active state. From this active state it will move to the partially committed state when it reaches to the last instruction of the transaction, and after performing the commit statement, immediately it will move to the commit state. So this is a normal a successful transaction goes in this direction. So now there are some other alternatives during the failures during the transaction failures. So it will take some alternate paths. So that is so when the transaction is in the active state, so assume that the transaction has completed all the instructions. When it completes all the instructions, it will move from active state to partially committed state, and before executing the commit statement, if there is any failure before performing the commit statement, if there is any failure, then immediately it will move from partially committed state to the failed state, and from failed state it will move to the aborted state. Here two things are going to happen in this state. So in aborted state, the first one is the transaction will be restarted if possible, otherwise the transaction will be killed. So this is one way, this is one direction where when the transaction fails. The other direction here is, so when the transaction is at the initial state, that is in active state, and before performing the last instruction of the transaction, say for example in our example we have 6 instructions. So before completing the 6th instruction, if there is any failures, then immediately the transaction will move from active state to failed state directly. So here, so if the transaction executes the 6th statement, and if before performing the commit statement, if it fails, then this will move from active state to partially committed state. Now in our case, the transaction has not yet completed the 6th instruction, so it will move from active state to directly to the failed state, and from failed state it will be moved to the aborted state. And as I told you just now, here two things can happen here. One is the transaction can either restart or else it will be completely killed. So this is how a transaction will move from one state to the other state during the transaction execution. So this we can also call this diagram as a state transition diagram. The next important topic here is serializability. So here in serializability, mainly we are concentrating on concurrent schedules. So we'll see here, we'll start with some basic assumption that each transaction preserves database consistency. Thus, serial execution of a set of transactions preserve database consistency. So now coming to this formal definition. So a schedule is serializable. A schedule is serializable if it is equivalent to a serial schedule. So when do we say a schedule is serializable? So when it is equivalent to a serial schedule. So here we have different flavors of serializability. So one is the conflict serializability and the other one is the view serializability. So in detail we will discuss about this conflict serializability and view serializability. Coming to this conflict serializability. So before defining this conflict serializability, first we will see what is conflict equivalent. See the definition here for this conflict equivalent. If a schedule S can be transformed into a schedule S dash by a series of swaps of non-conflicting instructions. So in the previous class, so we have discussed about 4 conflicting instructions. Out of the 4 conflicting instructions, so 3 are conflict and so one one instruction does not conflict and the remaining 3 conflicts. So based on this series of swaps of non-conflicting instructions, so we say that S and S dash are conflict equivalent. Now by this, okay, we can derive our definition. So now here we say that a schedule S is conflict serializable if it is conflict equivalent to a serial schedule. So you can see here one small example here. So now there are 2 schedules here, schedule 3 and schedule 6. In schedule 3 I have taken 2 transactions. Now what I am going to do here is, so based on the non-conflicting instructions, so I am going to swap T1 instructions and T2 instructions, and I'll convert this schedule 3 into schedule 6. So how I'm going to convert this schedule 3 into schedule 6? Based on the non-conflicting instructions. Either I can convert this schedule 3 as T1 followed by T2 or T2 followed by T1. So so this T1 followed by T2 or T2 followed by T1 is called as a serial schedule. Now you can see here in our example, schedule 3 is not serial schedule, but whereas when after converting this schedule 3 using non-conflicting instructions, so we have made it as equivalent to serial schedule, right? Equivalent to a serial schedule. So this is the one example of conflict serializability. So here, as I told you in the previous definition, you can see if a schedule S can be transformed into a schedule S dash. So in our example, S is schedule 3 can be transformed into a schedule S6 by a series of swaps of non-conflicting instructions. So that's why we say that so S3 and S6 are conflict equivalent. So based on this definition, we can derive this conflict serializability definition. So now we say that a schedule S3 is conflict serializable if it is conflict equivalent to a serial schedule. Obviously, as I told you, so S3 is a conflict equivalent to a serial schedule. So this is about conflict serializability. And now here we can see, so this example is a non-conflict serializability. See here, for example, if you take 2 transactions T3 and T4, so here T3 is performing read of queue and T4 is performing write of queue. Now as I told you, so we have to take this sequence. So in this sequence, okay, if this sequence is non-conflicting, then we can swap T3 T4 up and down. So you can see here the condition here is, so both the transactions are trying to read, are trying to access the data item Q, and one of the transaction is performing write operation. So this we used to call it as conflicting. So they are conflicting. So non-conflicting means, so here the data items should be different, and you can have any read or write operations here, or you can have so if the data items are same, So you should have only read operations at T3 and T4. So then only we can say that it is non-conflicting and we can swap. So in our example, so if you take in this sequence also, so here data items are same and we are having write operation, at least one write operation is there in this sequence. So either in this way if you see, or if you see in this way also, we cannot so we cannot swap this T3 T4 or T4 T3, we cannot convert. So we are unable to swap instructions in the above schedule to obtain either the serial schedule T3 T4 or the serial schedule T4 T3. So then next coming to this view serializability. So here I'm going to take two schedules here. One is S and the other one is S dash. S and S dash. See here. So let S and S dash be two schedules with the same set of transactions. So whatever the transactions we have in S, the same set of transactions we are going to take in S dash also. And now we'll see how we can define this view equivalent. So S and S dash are view equivalent if the following three conditions are met for each data item Q. Three conditions. What are the three conditions here is, so if in schedule S transaction Ti reads the initial value of Q, then in S dash also Ti must read the initial value of Q. So in S, okay, if Tj is reading initial value of Q, then in S dash also Tj only must read the initial value of Q. So whatever happens in S, the same should be happening in the S dash also. The second one is if in schedule S transaction Ti executes read of Q and the value was produced by transaction Tj, if any, then in schedule S dash also the transaction Ti must read the value of Q that was produced by the same write of Q operation of the transaction Tj. So for example, if you take T1 and T2, so if T1 reads any data item, okay, then T2 should be written that particular data item. Now when you come into this third one, the transaction that performs the final write operation in schedule S must also perform the final write operation in the schedule S dash. That means, so now for example, if you take Ti and Tj, two transactions, so in a schedule S, okay, if Ti completes the final write operation, then in S dash also Ti is going to end with the final write operation. Another example if you take, so Ti and Tj, so if Tj has executed the final write operation in a schedule S, the same thing should happen in S dash also. In S dash also Tj has to perform the final write operation. So if these three conditions are satisfied, then we can say that that particular schedule S is view equivalent. So now coming to this definition now, a schedule S is view serializable if it is view equivalent to a serial schedule. And there is another important point here is all conflict serializable schedule is also view serializable. Every conflict serializable schedule is also view serializable, but reverse is not. But we cannot say in the reverse, it's not vice versa. So you can see here the below example. So so this is a view serializable but not conflict serializable. Why? Because for example, if you take this T3 and T4, so T3 is accessing the read of Q and this T4 is trying to perform write of Q. So here this is conflicting, so we cannot swap. If you take this sequence also, so it's not possible. Or if you take this sequence T3 and T6, if you take here write of Q there, here also it is not possible. So this can be a view serializable but not conflict serializable. And another important point here is every view serializable schedule that is not conflict serializable has blind writes. You can see in the above example we have blind writes. Okay, so with this we will so this is the end of the view serializability. So so in serializability, so we have two types. One is conflict serializability and the other one is the view serializability, and we have discussed the examples and all, right?